You grab the watering can, you tip it over the bed, the water disappears into the soil. Job done, you think. But it isn't done, not even close. What happens in the 30 seconds after that water hits the ground is one of the most complex chain reactions in all of nature, and most allotment holders never see it. Start with the surface. If your soil has any kind of crust on it, which most UK allotment soil does by midsummer, the water doesn't just sink in. It hits a barrier first. That crust is called a soil cap, and it forms when rain or watering dislodges fine particles that then dry solid into a sealed layer. Dr. Lydia Burgess-Gamble at the Centre for Ecology and Hydrology has described this sealing process as one of the most underestimated problems in small-scale food growing. You think you're watering your plants? You're actually testing whether your soil can receive water at all. When the water does break through, it doesn't move straight down. It follows the path of least resistance. It finds the cracks left by worms, the channels where old roots have decayed, the gaps between aggregated particles of sand, silt, and clay. This movement has a name, preferential flow, and it means the water in your watering can is almost certainly not going where you aimed it. Here's what that means for your roots. Most vegetable roots, brassicas, alliums, beans, are concentrated in the top 15 to 30 centimeters of soil. But if water is flowing preferentially down old worm channels, it could bypass that entire zone and drain deep beyond root reach before the roots ever register it. You watered the plot. The roots stayed thirsty. This is not a failure of effort, it is a failure of physics. The solution isn't to water more. It almost never is. Research published in the journal Soil Use and Management found that slow, low-volume watering, what horticultural scientist Professor William Davies at Lancaster University calls deficit irrigation, triggers something remarkable in plant physiology. When roots sense mild moisture stress, they send a chemical signal upward through the stem. That signal is abscisic acid. It tells the leaves to partially close their stomata, reduce water loss, and redirect energy toward root growth. The plant, in other words, responds to mild dryness by growing more roots to find water on its own. Heavy watering suppresses that signal entirely. You water generously and the plant never bothers to deepen its roots. Drought comes. The plant has nowhere to go. This is the counterintuitive truth at the heart of UK allotment watering. A plant that has experienced mild, managed water stress builds a deeper, more resilient root architecture than one that has been kept perpetually moist. Your goal is not a wet plot. Your goal is a plant that knows how to find water. Now think about what happens at soil level when you water. The water carries oxygen into the soil as it moves, but it also displaces the air already present in the pore spaces between soil particles. If you overwater, if those pores stay filled with water for too long, you create anaerobic conditions. Roots need oxygen. In waterlogged soil, roots begin to suffocate within 24 to 48 hours. The same logic applies in heavy clay soils after rain. Your plot can look fine from the surface. Underneath, root cells are already dying. The microbiome responds too. Soil bacteriologist Dr. Elaine Ingham's work on the soil food web has demonstrated that the moment moisture levels shift, microbial populations restructure themselves. Aerobic bacteria, the ones that unlock nitrogen and phosphorus into plant-available forms, flourish in well-oxygenated, consistently moist soil. Waterlog the soil and they're replaced by anaerobic bacteria that lock nutrients up and in some cases produce compounds toxic to root tissue. Your watering regime doesn't just move water, it shapes the invisible ecosystem your plants depend on for food. What about the surface after watering? Watch carefully. The water beads on dry soil before it soaks in. That's hydrophobic soil, a real and common problem on allotment plots that have been left to dry out between waterings. Organic matter in dry soil develops a waxy coating that actively repels water. The technical term is soil hydrophobicity, and it's documented extensively in studies by the Royal Horticultural Society. A hydrophobic plot can receive an entire watering can's worth and funnel 90% of it straight off the surface and into the paths, away from roots entirely. The fix is not to water harder, it's to mulch consistently, keep soil from drying out completely, and in stubborn cases to use a wetting agent like diluted washing up liquid as a temporary bridge. There's one more thing happening that you'd never guess. When water hits your soil, it triggers a pulse of microbial respiration. Dry soil holds dormant bacteria by the billion. Add moisture and they wake up, rapidly metabolizing organic matter and releasing a burst of carbon dioxide and nutrients. This phenomenon is called the Birch effect, named after the Australian soil scientist H.F. Birch, who documented it in the 1950s. That earthy smell after rain, petrichor, is partly the smell of those bacteria waking. You're not just watering your plot, you're ringing a dinner bell for an underground city. The most effective allotment waterers are not the ones who water most often. They are the ones who water slowly, infrequently, and deeply, allowing soil to partially dry between sessions, encouraging root descent, preserving soil structure, and giving the microbial community time to cycle nutrients before the next flush. A soil moisture meter costs less than £5. Pushed into your beds once a day for a week, it will tell you more about your plot than a season of guesswork. Next time you pick up that watering can, you'll know you're not just adding water, you're starting a chain reaction 30 centimeters deep, one that will shape your roots, your soil life, and your harvest for weeks to come. The water disappears into the soil, and now you know exactly where it's going.